wasn't recording that whole thing. Toward the end of class. This class gets out at 12:30. And we use pots a lot because they're very cheap. Now, pots are contact devices, right? You understand? They got to make physical contact with what they're trying to measure. So we either do this through gears, or we do it through belts, or we do it direct contact.
This is what I don't know if it works. I'll try to fire it up on the next page. So this is, oh, I don't care that I do that. So this is a little circuit that we used to use.
But what we have is we just have a motor. It don't look good, but it works okay. It might work okay if something hadn't been pulled out. But, this is what I was telling you about last class. So we got a DC motor, and then we got it just taped to a pot. So there's the pot. And then we got a reference pot over here that I turn. And if I hook it up, when I turn the pot, the motor turns with the pot. That's going to vibrate a lot because of the type that we got. I'll try to. I think I got my power. I think I got it labeled. So this is the little comparator right here. I'm trying to see if it's a 301 or a 741. This guy right here. So what this guy right here is doing is it's comparing the output of my potentiometer to a set point. So I'm setting my set point with a watt, with a pot. And we want the motor to be able to turn back and forth. And I don't know the size of the pot, but it's all calculated out. There's my drawing page right here. So the actual circuit would look like this. So I've got a pot, and I put it across. I got a plus 15 volts up here. I got a minus 15 down here. And then my pot feeds into my error amplifier. And then this comes out, and we have two control devices that controls the direction of the motor. So one turns on with a plus, and my motor's connected right here. And then we got the other one that turns on with a watt, minus, yeah. This is minus 15 volts. These are actually transistors, guys. And then a motor, armature would be right here. And then mechanically connected to the armature, we have the pot. Oops. And the pot's a crosswalk, plus 15 and minus 15. And then the output of this goes over here and feeds into the other input of my error amplifier. By the way, we have two types of feedback. We have what they call negative feedback. And you can see this is coming into the minus end. Regulators, we use negative feedback. So if you try to speed up, the feedback tells it to do what? Slow down. If you try to go down, the feedback tells it to speed up. So this is the way this would work. So I'd set a voltage in here, right? Let's say minus 3 volts. That would turn on this guy here. It would output a certain voltage. And then the motor would start doing what? Turning. And then when this gets back to minus 3 volts, what does it do? Stop. So you'll see when I turn the pot, when I get time, I'll probably try to do this while y'all are in lab. When I turn the pot, the motor follows the pot. It's a very simple application of a sensor. Okay, so this would be the sensor. This would be what we call our set point, right? This right here would be the feedback. So this would be what we call a closed loop system, right? That's going to oscillate. Because motors, once they go in motion, they want to overshoot. And when they overshoot, the feedback sends are overshooting and pop back. So the motor's going to sit there and do that. Now, in true control, we use the same technique, but we use a technique called PID, which is proportional integral derivatives. We might have time to talk about that, where you actually compensate and keep it from doing wrong. So you understand what's going to happen with motors, right? So I come over here and I tell my motor I need to turn clockwise. It starts turning. The motor starts turning. And it's got inertia. What's it going to do? It's going to overshoot. Then I have an error. Then what is it going to do? It's going to compensate and it's going to overshoot. And then what is it going to do? So you'll notice it's the whole motor the whole time going to, but it's going to follow it. It's just that it doesn't have the right control in it to do the called PID. Y'all can do some research on that. So normally we use a PID controller for dealing with an analog device like a motor or something. So the next thing we'll look at is encoders. These are digital. What's about using a potentiometer is that if we input it into a computer, what's the first thing we're going to have to do? We got to convert it to digital, right? Computers don't know analog. We'll have to run it through an A to D converter. Sometimes it looks like they do, but they have internal analog to digital converters built into it. Analog inputs are becoming pretty standard on the PLCs. Analog outputs are not, because we can run an analog device off of a digital signal. So we have two types. We have absolute encoders and we have incremental encoders. So an encoder is in digital. It means we take some quantity and convert it into a digital form. So we're going to have an absolute encoder and an incremental encoder. Two subcategories of these would be what? Rotary and linear. In fact, we got that. We got an old dot matrix printer, not a dot matrix, but an inkjet printer that went bad on us, and we took it apart. And we can actually see the encoders. We've got both incremental encoders and linear encoders. So what we need to do is understand the difference between an absolute encoder and an incremental encoder. So this is an absolute encoder. This is binary. So what we do is we have sensors, usually light sensors, by the way. They shoot beams of light through these. These are usually clear, and then they got some black dial. A lot of times these are actually plastic. They may be metal rings. I've seen metal rings before where they do that. And what happens is I would start off, if I'm in this position right here, then light would pass through all these bands, and I would get back this number right there, right, which would indicate the position of the encoder. Well, what you got to do is you got to visualize the encoder turning. So what would happen is if I moved in this direction, then one would move under my sensors, and we would see that as a what? A 1, 0, 0, 0, and this would be, we would know it was at what position? Position 1. This would go 0, 1, 0, 0, which would be 0, 0, 1, 0. So this would equal to a 2. You understand that? Everybody okay? And if it turned again, it would give me back a what? 3. If it turned again, it would give me a 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is a 4-band encoder. So it would give me 16 combinations. But what if I turned it this way? Well, if it was sitting on 2, it would go back to what? It would go back to 1. So this guy here not only tells me a position that it's in, it also tells me the direction that the device is moving. Everybody understand that? But the problem is it's got a very low resolution, right? We only got 16 positions to represent 360 degrees. So what would be my resolution? So my output, if it's in degrees, And then I have 16 inputs, and that would be my resolution of my encoder. Very, very poor. So if my device was somewhere inside here, then all we would know is that it was at position 1. Unless I did what? Well, how do we get the number of positions? By the number of bands. So here I have 4 bands, so that's going to be 10 to the 4th. That would give me 16 positions. What if I added another band? And then that would give me 32 positions, right? Understand? If I added another band, it would give me 164. If I added another band, it would give me 128. What's going to happen is my sensors are going to have to be have a better resolution, because this inside band is going to keep getting what? Smaller and smaller and smaller. Either that or we're going to keep going out real far, right? You understand that? And what another advantage of an absolute encoder is that if I turn my piece of equipment off and I turn it back on, it knows where it's at. Right off the bat. All it's got to do is read that encoder. The encoder is going to give me back a number. The number says, okay, this is where my actuator's at.
If it was in position 2, and you turned it.
Well, in this way, this would be counterclockwise. So if I was turning in counterclockwise, the counts would go up. 0, 1, 2, 3, 4, 5, 6, 7. If I turned it clockwise, the counts would go down, right? 15, 14, 13. So when it starts turning, not only do I know where it's at, but I also know the direction it's moving at, right? Understand? Which is pretty neat. So a lot of times sometimes we don't need to know the direction. All we need to know is a position. But if I got my printer's skirting across that page, right? You understand? And I'm going this way, and most inkjet printers not only print left to right, they also print what? Right to left, and it's got to keep up with print positions, and it's got to know the direction. Now that's not hard to do, because the computer is telling the printer, or the processor inside the computer is turning the motor on either to send it what? To the left and send it to the right. But an absolute encoder, it would tell me not only the position that I was at, but also the direction that the count was going, right? So we could verify it. So if I told it to go clockwise, we could verify that it's doing what? Clockwise, or left to right. This is a rotary encoder. We could just as well do that with a linear encoder. This is a rotary encoder. So whatever it's measuring, what it's doing is it's doing what? It's turning this field. So this is how many bands? So we got 1, 2, 3, 4, 5. I can't count that. Right. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, these are not bands. I'm sorry. 1, 2, 3, 4, 5, 6 bands. So this guy here would have a resolution of 32. So it would take 360 degrees and do what? Divide that into 32 positions. Now, sometimes they'll put what they call an index mark out here. So they'll put another band out here let's stop it. I think I can stop it. So they'll put another band out here, and it'll give us a pulse every time it rolls around to 0. I think this is pretty close to 0. But it would only give us 1 pulse per revolution. And then what they would do there is they would have external counters that would count the number of resolutions to come up with the actual number. And that way we can get by with having fewer bands, right? You understand? But still, if I want a higher resolution, I'm going to have to put more bands, period. Because we got to get them closer together, right? The 0 count has to be closer together. And this goes least significant bit to most significant bit in this direction. So what's it seeing right now? Well, here, these represent 1. This represents a 0. This would be the most significant bit. This would be the least significant bit. So I'd be at 0, 1, 0, 1, 1, 1. What? Yeah, the reds are zeros here. because it's blocking the sensor. So these use light sensors. So normally they use light sensors. So we can use magnetics. We'll look at those too. So light sensors, what it does, it shoots a beam, and when it comes through and strikes the sensor on the other side, it will take it as a 1. Well, I got it backwards, right? I said that right. So this would be a what? This would be a 0, 1, 0, 1, 1, 1. What's 16 plus that? 23. What you watch when it's in rotation, I mean, it's constantly changing according to what's moving the encoder. Now, what would happen on this one? This would be a 4-band encoder, but it's a linear encoder. So if I was going to use a linear actuator on a rotary encoder, what would I have to do? We'd have to go through something that takes a linear motion and converts it over to a rotary. What we call the device that does it? Oh, rack and pinion, right? We can use a rack and pinion. What we're doing on our conveyor belt over there, we have a conveyor belt over there, and it's got an encoder on it. And all they do is they've got a nice rubber wheel that rides on it. So as the conveyor belt is moving, so it's kind of like a rack and pinion, right? But a rack and pinion is 2 gears. And then the encoder would be connected to the pinion, and then the device that's moving would move the rack. But this is what they use over there. Very simple. It's a wheel that's riding on the conveyor belt, and it turns. It's turning the encoder, and the encoder's telling me the position of the belt. But it not only the position, it could also be indicating what? The speed. How fast those numbers go by would be an indication of speed. Of course, the one we would probably use for speed would be this little one out here, because this will give us the best resolution of speed. So I could just watch this bit right here change, and I could look at the time it takes for it to change. If I know how many slots there is, then I can calculate the speed. So these are absolute encoders. So what's the advantage of absolute encoders? Well, the advantage of them is, number one, is that they provide a position even when power's been off. Right? You understand that? They provide an absolute position. That's why they're called absolute encoders. So I can turn my machine off anywhere. Your printer does not use an absolute encoder. It uses another one that use that. So that means every time you turn it on, it's got to find itself. So what does your printer do? Every time you turn it on, it goes, you hear it finding itself, because it doesn't use an absolute encoder. The problem with absolute encoders is they're very expensive, because number one, to increase the resolution, you got to put more bands. Every band's got to have its own sensor, so it's got more electronics involved, right? Then we got to run wires from all those sensors into our control system. But what's nice about these is we're getting a digital number out of it, right? We don't have to go through an A to D converter. We're getting a digital number right off the bat that represents our position. Now, if I was representing speed, I would have to count. We'll look at that in a minute. So we don't have any absolute encoders over here. All we got is the next one we'll look at, but they're out there. Right? Are you okay? The next encoder, which is the predominant encoder now. So this is accounting in binary. So this would be a 1, 2, 3, 4, 5. So I should have added one more because that was a 6 band. For some reason I came up with 5. So with 5 bands, what we have is we have 32 combinations. Right? Understand? And then each combination would represent a number. The problem we have with these guys is in digital, how long it takes to move through the digital circuits. We call it the propagation delay. This is how long it takes an output to respond to a change in input. Okay, you understand that? Now the problem is, here we would be going through 5 different circuits to keep up with this. So the more bits that change inside this number, the longer the propagation delay would be for the output to respond to the input. This makes sense. So I look at a 0, from I go from a 0 to a 1, how many bits change? Okay, 1 bit. When I go from a 0 to a 2, how many bits change? 2. Because this one had to go to a what? 0. This one had to go to a 1. When I go from a 2 to a 3, how many bits change? 1. Yeah, this guy right here. This guy here stayed the same. When I went from a 3 to a 4, how many bits had to change? 1, 2, 3. We had to have a 3-bit change. When I went from a 4 to a 5, how many bits? 1, right? When I went from a 5 here, we had a 2-bit change. So what's going to happen, you see this varies all the way down the line. When I go from here and I was to rotate around, we would have a 5-bit change. So we would have a large propagation delay. So the more bits you have changed between counts, the worse off that you might be missing counts at high speed. And you see some of these devices, when they move, they do what? They move. Everybody understand that? So what they did is this is a weighted code. I mean, you could figure out these weights by doing what? 1, 2, 4, 8, 16. I'd add 16 to 8, I'd come up and get what? 24, and that would be the decimal weight of that number. So this is binary. Binary is a weighted number system. Each bit has a value. But we use code. What is a code? When we talk about code, what's a code? It's a representation of something else, right? You understand? So a computer's got to represent all different types of things besides numbers. When I look at my keyboard, on my keyboard, I see A, B, C, D, E, F, G. I see all these. Those are not numbers. Those are letters. Well, how do they represent that with binary? Well, they got a code. So when I press the A key, the keyboard sends a code to my computer. It's 1s and 0s that lets the computer know I pressed the what? Letter A. It's a key scan code. We could go up there and we could go on the internet and look at the key scan code that would give us the code that this computer sends for every key I press. And it's not weighted. It's just a what? Code, so key scan code. And then we'll just look at images. So here's the key scan codes. So there's a code. I can't blow this up, guy. But there's a code for what? For every key. And this is what, so when I come over and press this key, so if I wanted to come up with something that would count that had less bits that changed, then I could come up with a code. Well, they came up, and it needs to be a standard so I can have other electronics besides mine respond to this. So the code they came up with was a code they call the gray code. And it's a counting code. It's not weighted code. So codes, what are codes? It's when we use, a code is when one thing is used to represent. The dominant code used in binary or ASCII. But when I come up here and type stuff, and it's displayed up here on the screen, is it a U? No, it's the code for a U. I don't know if you can see this if I come up here and was to come in here and I was going to come, so I can come up here and I can insert what we call a symbol. So when I come up here, I'm doing the not equal to. What does this application see? It don't see a squiggly line. It sees this code reference. And this is a hexadecimal code, by the way. It's not decimal, even though it looks like that. And I could come down through here to all these different things, and it would come up here. Let's see if we can find. So 253C, that's a binary code. It's a 16-bit code. That means we could have 65,536 different characters using a 16-bit code. They don't show you here. Yeah, it is. What code is this? Now this is Unicode, but they're not giving you the binary code, which is what the computer's using. They're giving you hex. Why? For us, right? It's not for the computer, it's for you. Because if I was to convert that over to binary, 253C. So y'all deal with this all the time, but you just don't kind of realize it, right? So 253C, anybody can do that? 2, 5, right? 3, C. So that would be the actual binary code that it's actually transmitted inside your computer. When I come up here and type the letter A, get the code from my keyboard, and then it translates that into a Unicode, right? That's the beauty of the computer. It can translate things into almost anything. That's why a lot of times you can go to a web page and have it translate, right, into a different language. So Unicode is the primary code we use a lot on the internet, like BCD, which is a method of representing unweighted decimal. And then the code we're going to look at is this code called what? Gray code. Gray code is used for counting. The advantage of the gray code over counting in binary is that only one bit changes between counts. Is that counting up or counting down? Shouldn't make any difference, right? So this is the code for a 0. Everything looks okay so far. How many bits change? Of course, we don't know. How many bits change from a 0 to a 1? How many bits change from a 0 to a 2? So that, if I converted that to decimal, that's going to be a 3. But this is not a weighted number. This is a code. So this is the code for a 2. This is the code for a 3. This is the code for 4, 5, 6, 7, 8, 9. And I go from a 1 to a 2. How many change? 1. I go from a 2 to a 3. How many change? 1. I go from a 3 to a 4, how many change? 1. I go from a 4 to a 5, how many change? If I go from a 5 to a 4, how many change? 1. So using gray code, no matter which way you count, you only have a what? A 1-bit change. And what's the advantage of that? Well, it's a lot faster. So a lot of your counters or a lot of your devices that'll give you out. So I get some absolute encoders, they give me gray code. And that's something you got to understand, right?
I don't understand.
What do you mean?
I understand 1. I understand 2.
What's your trying? Okay.
But 3. I see a 0 and a 1. You're trying to weight that number, but it's not a weight, it's a code. It's a code, right? You understand? Right? But you say what's different?
Well, it's a different code. This is the code for a 3. All we're trying to do is, okay, so I had this bit right here was a 1, this bit right here was a 1. This right here was a 1, this is a 0. How many bits changed? 1.
Oh, okay, I see.
Yeah. Over here, this is a 1, that's a 1. This is a 0, that's a 0. This is a 0, that's a 1. Which one changed? 1. Okay?
Okay, so it's really not
counting.
counting.
It's not counting.
It's just a code.
It's a code.
Gotcha.
That's exactly right. It's just like an uppercase A is this code right here.
But the top it starts at 0.
Yeah, 0. That's what gets people confused.
So when you go down through there, you hadn't done 6 yet.
So. It's going to be 1. So this one's the same. This one's different. This is the same. How many change? 1. Okay, see that. But just like this, if you tried to do that in decimal, that's not decimal, that's a code. That's a code that's the ASCII code for the letter A. It's not a weighted number anymore, right? You understand that? It's a code. So we use codes. A computer's got to use codes to represent things all the time. Because I don't just deal with weighted binary. So we got instructions that we tell the microprocessor what to do. Those are called operational codes. So if I wanted to tell the microprocessor to add, I can't say add. It don't know what this sign is right here, does it? So I send it a code that tells it to do what? Add. And we have these opcode charts. We have these, they're getting more complicated now because we're dealing with 64-bit programming, right? So your operational codes can be used. So we can tell these processors to do all kind of stuff now. But if I wanted to find out what the code for add was, odds are I got 15 different ways I can add, right? You know, I can add with carry, I could add this, I could do that.
And and if I was writing in machine language, I would have to figure out what? The codes. So if you actually look at a true binary, a true language that the computer understands, it is binary. It is not add, it is not subtract, it is not move. So in PLCs, when you put a move in there, you're doing it in English, right? You understand. But the computer, the processor sees it as a what? As a binary code. We call those operational codes. You don't see many people doing machine language programs anymore because of the complexity. So we used to have these charts, and we'd say, okay, I want to add, and what would I do? I'd look the binary code for add, and then I would enter that into the memory, which is what's in memory. So memory's got all these codes in there, right? You understand? And we could dump some memory out and let y'all look at a program if you want. You can't do it on this machine. There used to be a program out called Debug, which allowed us to dump memory. We could dump memory. We could put stuff in memory that I wanted to. We could do, and it was so dangerous because people would screw their computers up because you was inside the machine. So they got away with that when they came out with Windows 7, but they still supported it on Windows XP. I can connect to this computer. This is a computer over in so this is the computer that's over in the I hope somebody's not over there using it. No, nobody's over there. That's right. Hoyt's on the Birmingham campus this semester. I'd have to remember the codes. We used to all the error codes that used to pop up when you had disk errors. We figured out where all the codes were on the disk, and we went in there and changed them. So it would say, you know, like you're doing the wrong thing, stupid, and stuff like that and stuff.
You could have just put what was wrong, what the error was.
No, but that's what was there. We went in, we knew where they was, we knew where they was at in memory, and we had the ability to go out there and change them. So it's staying.
So when it gave you an error, it gave you a code?
No, it was stored in there in the letters were actually stored in there using a code.
You could figure out.
Yeah, and all you needed, the codes were easy. They were nothing but ASCII code at the time. Huh? What do you mean?
You know what I mean?
Well, everything a computer does is codes. And those codes are written by somebody. So it looks to us like it's true artificial intelligence, and eventually it will be. But what you've got is you've got a person that's very, very smart that's tried to figure out the code for all these different all these different things that could happen. And then your program makes decisions on which code to run depending on what it gets from its sensors or where it gets from its input. I mean, it's a perfectly legal question. So we still have command prompt available, by the way. So when we had computers, originally when the computers first came out with IBM, this was what we saw right here. Yeah, this was DOS. And it uses the shell was a text shell, which means you had to type in every command. And so if I wanted to run a program, we'd have to know the name of the program. And this is debug. And then I could come up here and I could dump, with just a whole bunch of memory. Oops, I dumped. I gotta remember the syntax. I don't think you put a dash. There it is. So this is memory. And of course, it's not going to display it in binary. It's going to display it in one hexadecimal. So this is what the computer sees. So everything has got to be represented with a what? With a code, right? Y'all understand that? And everything in the computer has an address. If I got this right, it's been a long time. Okay. So what I've got right now is I'm looking at the memory in the computer that runs the display. What it's showing me is showing me the contents of the display memory, which is 4D. Now, if you had an ASCII code chart, if you look up 4D, this is hexadecimal. It would be the code for the letter N. If I wanted to change that, then I have to know the code for another letter, and that's what it's waiting on. So I'm going to put 41, which is the code for letter A. And what you'll see, the M up there, y'all see what I'm talking about, upper left-hand corner, and I'm going to hit enter. What did it change to? An A. So what my program does, when it displays information on the screen, it's sending codes to the display, the computer or the processor that's running the display. That's all it knows is codes, right? And then it translates that code into a pattern of dots. So we use in computers, we use codes all the time. And then I can make it do neat stuff. Oh, I didn't get space. I messed up. I didn't have to put all zeros. Oh, no, I want to enter into memory the text memory. This is the text memory on the display. This is not the graphics memory. Enter the, oh, I made a wrong syntax error again. Colon 0. Now it's got 41 in there. I could come up here, and I would have to look up the codes too, but I could change it to another letter. So if 41 is an A, what would 42 be? A B. But here I'm going to hit the space bar, and it changed to a B. Then I don't remember the code, but I'm going to enter another code here. And what I'm doing is I'm setting the attributes for the character. And so notice the background and the foreground colors change. I don't know if you noticed that. So not only do I have to set up, I have a code for the character itself, then I've got a code for what we call the attributes, what it looks like. We can make them blink and flash and stuff like that. But what we're trying to get through here, that everything the computer does, if it's not math, it's going to be what? Code. Codes to tell the video display controller how to display these dots to do different things. And that's all built into the application and what type of video controller that you're using. Fortunately, the same brand computer usually uses the same codes. And then we have a driver that runs the display, right? You understand that? So this is actually what's going on. So what we did is we figured out where all these error messages that pops up on the blue screen, we figured out where they was, and we went in and we changed. But hopefully that gives you a feel of what codes and the way a computer works. So it was obvious that they had to come up with a code that the input to the computer could keep up with without going through all that propagation delay. So they came up with a counting code called the what? Gray code. I don't know the gray code. I'm sure if I dealt with it a lot, but it's just like anything else. If I didn't know the code, then hopefully I've got a chart somewhere that tells me what the code is, right? You understand? And it's just like when I clicked on that unit. And there's a way, guys, that I have to go back and look at it, that you can, instead of entering the letter A, you can tell your computer the code for the letter A, and the A would pop up there if you was using Microsoft Office, because it's binary code, right? You understand that? Y'all could go and research that if you want to. But this guy here uses a code called Unicode direct. So Microsoft uses a code called Unicode to represent what? I mean text, not the this is graphics. So we got two types of memory inside the computer. We have text memory and then we have graphics memory. Graphics memory is we turn on dots. So that's gray code. We did all that on gray code. So this is a gray code encoding. So for me to understand this, it, this would be the same encoder, but this is in gray code. And what we would see between every position, how many bits to change. be just what I want. But what's the advantage of an absolute encoder? We tell the direction, but we know the position. So we know the position even if we have to turn the equipment off. So if your printer had an absolute encoder on it, it wouldn't have to reset it every time you turned it on. Or it wouldn't reset every time you restarted your computer. So every time you restart your computer, what does your printer automatically do? It finds itself. It wouldn't have to find itself if it had an absolute encoder. Wherever that print head was at, when you turned it off, when it turned it on, it would do what? It would know it was at that spot. And what's the disadvantage? What does that translate to? Cost. Yeah, it's more expensive. It's just like if our network, if our wired network was a parallel network, it would be a lot faster, but it would cost a ton of money to run parallel wires. If every channel coming to the back of your TV had to have its own cable, right? You understand? We wouldn't have 200 channels. It limits the number because that'd be impossible for them to get all those wires out there, right? You understand? So this is an absolute encoder. I can't tell the band. I think it's 1, 2, 3, 4. And this looks like it might be the index band. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's 10. I think it's a 10-bed encoder. So that would be this. But you can see these out here, these ones, they get what? Very, very small. So if you ever looked at the encoder on a robot, the actual encoder looks like it's gray because of what? The bands are so close together. And this would be the actual output of binary. So it has electronics in here that would take the actual code and send it out. A lot of wires, a lot of sensors. Alignment is very, very critical. So the most popular encoder that we run into is what we call an incremental encoder. Let's see how this guy works. So we have some type of sensor. Could be light, could be magnetic. The most popular in robotics is light sensor. So we have a light source and we have a light detector. And every time a blade comes through, what does it do? Breaks the beam. Now, very simple, be cheap, a lot cheaper. But what's the problem with this guy? You're not limited by the number of bands. We do have an index node here that gives us a pulse every time it comes around, right? But what would I have to do to get a position out of it?
So what you say?
What would I have to do to get a position out of it? All it's going to do is give me a series of pulses. That's all it's going to do. It's going to give me a series of pulses. So what would I have to do with this? So how would I know it went to this position right here? What would you do? We started right here. How would you know it was in that position right there? Yeah, but how would you know? So you can't see this thing. All you're doing is getting pulses. What could you do to know it was at this position right here?
Set it.
I would count pulses. 1, 2, 3, 4 would indicate it was this position right there, right? You understand? 5 would indicate it was at the position right there. So I would count the pulses. If I can count the pulses and I know how many, well, I don't really need to know how many pulses we get per revolution, but that'll come into play when we start dealing with speed, right? You understand? But all I have to do is count the number of pulses. And then if I know the distance between the blades, then I can interpret that for what? A position. So all I have to do to figure out a position is to count. So what does that mean? We're going to feed these guys into. The output of these guys are they're going to be fed into a counter. And then the output of the counter is going to come into the wall, a position. right? And of course, the speed of the pulses, how fast they come in, would it be an indication of what? How fast it's going. So we get two things out of these. So when we get into speed sensors, we're going to bring these back up again. So normally we use this thing for two functions. Not only can we use it for speed, we can also use it for position. Now this guy right here, first of all, number one, before that count means anything, I gotta establish what we're counting from, right? I have to establish a zero. In robotics, this is what robots use. So we have to establish what we call an origin. It's just like me giving directions. I say, go down to the 5th red light and turn right. What does that mean to you? Unless I say from here, take a left and go down and turn right at the 5th red light. So anytime we're using incremental encoders, first of all, we have to establish a reference. We have to establish what we're counting from. So what's the first thing your printer does? It uses an incremental encoder. What's the first thing it does when you turn it on? Finds, it's got a sensor over there that establishes where zero's at. And once it's established where zero's at, then now what the count means something. So incremental encoders, we have to establish a reference that we're counting from. Right? Everybody understand that? So here, this right here could be our reference, right? Right? Does that make sense? But this guy right here would only take us in one direction. This guy here has no idea what direction it's spinning, and all it knows is what? Counting. You don't know whether to count up or you don't know whether to count out. All it's getting is count. So we would have to have something external that would try to figure out what the direction was. Now your printer's okay because your printer electronics is telling the motor to either run what? Forward or reverse. So if you run it one way, it's going to do what? It would tell the counters to count up. If you ran it the other way, it would tell the counters to count down. But it's still got to count from a position, right? What we call a point of origin. Everybody okay there? That makes sense. But the speed of the pulses would tell us how fast it was going. And then we could count the pulses, and it would tell us what? The position. Everybody okay? Does that make sense? So this is we call this a single channel. It's still called a single channel, even though we have two channels. We have this one and one for the index. So this would be an incremental encoder. So you can see the index mark right here. That's it. And this would be plastic, and then they just have bands. And then we have a photo sensor that sits under it, light source. Then we have a light detector on the other side, and it breaks, it gets pulsed off. And then the index hole would tell it every time it goes to complete revolution, right? It wouldn't tell it, I'm going in this direction. All it would indicate is I'm going. So these guys work out really well if we have something that runs in one direction all the time, right? Understand that? One direction all the time. But we have to have what on these then to get a position? You gotta have external count. You gotta count. PLCs look to count. These are very popular on PLCs. So what I'm doing is I'm getting a digital thing representing position instead of an analog value. So a pot would give me an analog value, and when I got it inside my PLC, I would have to do what with it? I have to convert it to digital for it to mean anything to my program. Here, this guy right here is going to give us a digital output. So here, all I've got to do is just count. I'll just bring this into count. PLCs have counters. If they're running real slow, then a software counter can keep up with it. Most of your PLCs now have hardware. Y'all know computers. Y'all understand the difference between software and hardware? What's software? Programs. What's hardware? That's circuitry. That's actual circuitry. The biggest disadvantage of software is that anytime you do something, you got to run through a module to figure out what's going on. So I've got a code coming in. Well, I need weighted binary. I'm bringing in gray code, so I got to run through a program, a little module that converts the gray code into what? Into binary. So when we start adding all these features like counters are pretty complex. Software counters are pretty complex. So that means the module that handles a counter is going to be fairly what? Big. And if we look at the time it takes to upgrade a counter, a software counter, it's going to take a while. So that means if I've got a motor running at, 3,600 RP revolutions per minute, think about the number of counts you would get per second. And most of your software counters inside PLCs cannot keep up with these encoders on these high-speed actuators. So what they started doing, and it didn't take them long to realize this, is they put high-speed counters in those. And those high-speed counters are not software. They are what? They are hardware. So every PLC that we have on this campus right now has hardware counter, has high-speed counters. And then if we needed to take the input of one of these things, we're not going to bring it into a regular software counter. We're going to bring it into one of our what? High-speed counter inputs and count those. And then we can just count positions real fast. So you see some of these robots, they move real fast over a distance. This is the old mics that we use, which is pretty neat. So I don't know if y'all can see the actual encoder wheel right here. See the pedals on? These were the two sensors. We'll talk about why they use two sensors. We use one for X and we use one for Y. And then you use the ball, and what does the ball do? Turn those encoders, and then translate it in X and Y to figure out where the mouse is at. And this is still basically what works, but here we're using optics and we're sensing impurities in the surface. It still kind of works the same way. But this is a perfect example of an optical sensor we'll look at later on. This is the one they use most often if they need to sense direction. We use what they call a quadrature encoder or two-channel encoder. And what we do is our two sensing elements are offset by 90 degrees. You see that? So what happens when this thing turns? So here V1 is going to lead V2. V2 leads V1. So it leads me, it occurs fast. And what we do on this is we don't look at the level, we look at the edge. So here when V1 goes low, this guy here is what? Low, yeah. Notice every time this goes low, this one right here is what? Low. When I come down here, every time this one goes low, this one right here is what? High. So what I'm doing digitally, I can look at it and we can reference it. So the timing is referenced to one of them. It's going to count one of them. That's not exactly true. Usually you hands them together and count them. But what we do is we look at one of the edges. So here they're looking at what it is, negative going in. And then what they're doing is they're referencing what goes on the other encoder when this is going on this edge. So look, we can tell the direction by doing what? So when this one's low, when this one goes low, this one right here is what? Low. And every time when this one goes low, this one right here goes low, which would indicate on this one that it's running in what? Counterclockwise. We spin it the other way. Now what happens when this goes low? So when this one goes low, this one right here is what? High. When this one goes low, this one right here is high. Right? So we can tell by the offset if it's in what directions it's going. So here we can use what we call up-down counters. And we can tell our counters either do what? Count up or do what? Count down. And then all we do, and by the way, quadrature encoders are so popular that most of your PLCs now give you the ability to use quadrature. It does this for you. It will give you the direction and it will give you the count. But this is going to take at least 2 of your ports on your PLC, right? Understand that? If it runs a quadrature encoder, because you got to have one for one. Yeah, for the direction, indicate the direction.
So in this case, up, down, comma, high speed, comma,
Well, it depends on how fast your encoder runs, or what the actuator that's in motion. You know, the actuator that's in motion. We have the ability, unfortunately, we don't have the ability to teach, especially motors. Motors, we want to do one of two things. We want to control its direction, or a lot of times we want to control its speed, right? And we want to know its position. If the actuators move real fast, then you're going to have to go to a high speed counter. Because the resolution, now what determines the resolution is how many of these dang blades you can put per circle. The more I put per circle, the slower I'm going to have to count, right? So if I've got one blade, then I'm only going to get 1 pulse per revolution. So if I was counting every 1 second, then when I come back to 1 second, that blade might not even be around there, and I would count a 0, and I'd get that one blade every once in a while. If I added 100 blades and I counted for 1 second, then I'm going to get 15, 20, 30, 40 blades even in 1 second, right? You understand? So what I can do now is I get more accuracy, I can run my motor slower, but now I'm going to have to go to a high speed counter because the software counter can't keep up with something. So like I said, just about every PLC now, I've been playing around with the high speed counters on the Micrologic 1100. Next week I'll try to bring that in and show you. And the software is very, very simple. trying to convert a pulse over to a RPM. And we'll show y'all this. We'll look up a incremental encoder and let you try to figure out the speed, but we'll do it in the slow state. I know we look at some crazy. But these are probably the most popular right here. If you need to do what? If you need to get position and direction and speed. Speed's real easy to do. A lot of times you'll see them use a dual channel because what happens, a lot of times you'll stop your motor. They'll use a dual channel even on a single direction. And the problem you have is when you stop a motor, a lot of times it'll sit there, a vibration. If you stop right on this blade and you're in an industrial environment and everything's out there vibrating, what could the motor do? The motor could sit there and be doing this, and if you're looking at that blade, what could it be doing? It could be counting. So a lot of them use a quadrature encoder. Use nothing but a quadrature controller, and then they'll only count something like this. So if this guy right here sat and did this, and this guy right here was in the center, it don't move, then you wouldn't count, right? So you'll see a lot of people will use a quadrature encoder, even if it's a single channel, even if all they need to do is turn in one direction. Because what you don't get is you get less invalid counts due to the vibration when the motor stops. Y'all understand that? So if you had one blade up there and your circuit was sitting there doing what? Vibrating, and what it could be doing? Yeah, it'd be counting every one of those. So you'll see a lot of quadrature encoders used on even though the motors only run, or the actuators only run in one direction. So these are quadrature encoders. So the one that's on the manufacturing line over there, even though the belt only runs in one direction, it's a quadrature encoder. It's almost 11 o'clock. We probably need to start working on all that. So let me stop this.